Welcome back, PlayBasic coders. Let's talk about some nitty-gritty stuff here. Today we're going to be looking at a way of doing allocations within a single array and treating that array as if it was multiple chunks of data. It turns out that there's a couple of these kind of systems that are in PB to manage allocations that are then chopped up and reused. The idea behind this is to eliminate dynamically allocating memory. When I was timing one of these routines, because I found a bug in it, it turned out that if you had a few hundred allocations, it could take seconds for this thing to reconstruct the buffer. Clearly, in a real-time situation, that's not good. So I went, that's kind of weird. And I thought, well, I wrote some of this stuff years ago in DarkBasic of all places, and the old libraries I had in those days had a kind of dynamic allocation within it, because the one that's in PB is doing a brute force. For a handful of buffers, it's no big deal. And that was the assumption, is that in that particular case, and that version of the library was using the mapping commands. It's kind of unusual for maps to be, to create hundreds of maps in memory at once. So you probably wouldn't run into the problem in that circumstance. I don't think anyone actually did. I didn't notice it before. I just noticed a weird bug where I was looking at some of the other command sets and going, oh, that shouldn't be a thing. And when I was tracing it through, I discovered that, oh, gee, this takes a lot longer to do a simple thing than what you would think. So I tracked down this old code and put a bit of work into it separately, because it's all about the logic. Like, what something is written in often doesn't really matter. It's about making that logic fit your circumstances. I'll run the test anyway. It's not a visual test, we're looking at just allocation of memory. Now, controlling this with the arrow keys, what we're seeing here is the overall block of memory visualized as it gets larger. So each color is an allocation, and where it occurs within the space in here. Green chunks are memory that's not used. So we could ask the system for, hey, give me this many bytes, and it returns the index or the address of that block of memory within this global array and this big chunk of data. So we're kind of treating a subset of that data as for our temporary use or longer term use, and then the system is shuffling this stuff around for us as our program runs. I've got a secondary key here to recompress or defrag the memory. So if I hit the left key, we get allocations. This is doing like 20 allocations and 20 deletes. So our consumption is getting higher and higher. So I give you the hot tip is that we're running at 20 frames per second in PlayBasic, right? We've got 2,000 of these things. Do a quick defrag. We've got 66 meg of memory being consumed in just PB code. Not C, just PlayBasic, simple for next loops, copying that memory around when you do defragmentation. When I tested the libraries that actually are in the mapping commands, to handle 1,000 allocations, it took 20 seconds or something like that, 25 seconds or something. That's how inefficient it was, yeah. So clearly this is much more efficient. This approach is much more efficient. That's why we get our net improvement. And the reason behind why it's more efficient is quite simple. Is it's not reshuffling all of the memory all of the time, and that's what the other system was doing. Because when it was when it was ported, I guess, originally from sort of DarkBasic days into C, it was simplified for that purpose. It was like, oh, well, it doesn't really matter if it's a bit brute force because, it's really fast and we can copy that stuff around. We're only copying small blobs of memory around here and there, but that's not the case. In the real world, that's actually not the case at all. We hit D, we just delete a bunch from the end of the buffer. So this green space represents 66 meg at this point here of memory we're allocating blocks from. This is randomly sized, and so we're doing a bunch of allocations each frame, a bunch of deletions. This ratio here is the fragmentation ratio. So just a way to visualize how many holes there are or gaps there are between the allocations in memory. That's all it is. Just did a defrag. So it's kind of the same principle, I guess, as doing like a disk defrag, really. We've got this block of memory, or we've got a disk, we've got a bunch of used sectors. We run through, we organize them, and then we just copy those sectors down and link them together. How does it work? Well, it's really simple. In this version here, there's nothing cute about it. We're actually using a classic two-dimensional array because this code made its way from DarkBasic, so we don't have types. I've cleaned it up a little bit, and I thought, no, well, I'll leave it the way it is. We've got some things there that are kind of superfluous because there was a need at some point to have two different types of memory, which that was necessary in the old version. We don't really need that in this version here. This is our heap, a global heap. So when we initialize the library, we're effectively dimensioning this library at some size. Look at the test code over here. We'll go to that code. So we're starting the library, we're allocating that array to be 16,000 cells. So when we call give us a new bank, it's going to give us a chunk of that, and if it's not available, it will resize the underlying array for us, and we don't have to think about it. We just we call this new thing here, and we get back a bank that we can then operate on as if it was our own individual piece of memory. The purpose of this really is to keep all of that memory that in a common place, so we get caching benefits from this. Rather than having blocks of memory all over the place, which may or may not be sitting in memory next to each other. So it kind of mimics the bank commands in PlayBasic. That's deliberate. So we're showing some basic stats, returning from the setup code here and going back to the main loop where we just got our controls, do a brute force. We're adding 20 new allocations if I press left, and then we're doing potentially 20 deletions the same frame. We're showing the bank order. If you're in debug mode, it's a bunch of stuff being pushed into the console. So I was having some troubles about overlapping banks. This is where this all started was I noticed there's some bugs in the actual mapping commands where those buffers could overlap, and I think it was probably in the real world sense it would have been very unusual for that to happen, but it was absolutely possible. I thought, well, I'll fix that, and I looked at that's what got me looking at the allocation code, going, oh no, this has got some pretty much classic sort of n squared problems where it's brute forcing its way through. Probably at some point I must have had the idea about I'll write a better allocator at some other point, but I just didn't. In classic application design, this is what happens. You eventually have to go, well, I better fix that. So this is showing our buffers. which indexes here represent the buffer and the size of that buffer. So that one there's a 10K buffer, another 10K, 4K, 7K. So here the whole thing is scaled down to show the entire block of memory. This 11 meg block gives sort of a usage map, and it's a heat map too. So things in white are big chunks. The darker the color is, the smaller the chunk is relative to that. And if it's green, it's an empty space within RAM. But really, when we call our new bank here, it's kind of brute forced, really. We're doing a new bank. We just call our little. My naming convention here is the P represents a private function, so this is not something that you would be calling from the API, but you would be underneath. This is what actually is occurring. So it allocates the bank and then it fills that bank full of this value here. The allocation, let's have a look at it. So we're doing a straight, good old fashioned, we're running through and going, hey, give me something that's free, that's available in our bank structure. If we found one, let's just jump out here. Bit of classic go-to magic. If we didn't find one, let's expand that table and return the size of the table plus 1 as the next available bank. That's not the memory, it's just the handle we used to access the memory, because that memory is moving inside the main array. So we can't rely upon its location in RAM. So we have no kind of lock concept in this as well. So it's actually moving around. So every time we use this, we use a bank and we want to access the data within it, we grab the bank pointer, the address, the current address is going to be, and then we manipulate that data. But the thing's as straightforward as I can probably make it. We're looking for an unused bank at this point. No, that's false. If we find one, we just go, yep, cool. Then we look for a free block of memory that's of this required size. And the way it works is we're keeping two lists of banks. We're keeping a pre-sorted list of banks indexes. So they're sorted based on what address in memory they've been allocated to. So we're just sorting them in order as they appear, so we can step through them during this request and go, let's look for a slot, if there is a slot between the existing banks, and if we find it an appropriate place, this new allocation can go, we can slot it in that spot and return this address back to the user, back to the library. We initialize this new bank and then we add it to the sorted list. That's the allocation. So this find free is not pretty. We've got a few edge cases to handle. So we've got is the list empty? If it is, we just kind of add it to the list. There's another one that pops up is the first thing in the list, does it actually start at the bottom of memory or not? In other words, is there space to allocate the new thing at the bottom of memory? Maybe there is, maybe there isn't. And we set this to, there's 2 pointers here, there's 2 variables here I'm using as what's the address of the memory we're going to return back to the user as to where the new allocation will go. And we sweep through all the existing allocations looking for an appropriate gap size, or the smallest gap size where this allocation will fit. We don't have to do this, we can just kind of go, hey, just find a gap and stick it in there. Yeah, whatever. This thing, because the list is sorted, we could use a binary chop sort search here, but I haven't actually. My reasoning for not doing that really is that I'm thinking, well, at peak, this is going to have like 1,000 things in it, maybe. In the test here, it has like 1,000 things. If you keep going with the system, keep adding stuff, eventually your program runs out of memory anyway, so you end up with these huge data structures for no real purpose. So there's definitely a limit. I think it's in this version it's limited to like 65,000 banks or something, which is way beyond what you can have in memory anyway. Because if you think of it like this, I mean, each bank before was probably averaging about 5k in size, and you've got 2,000, 3,000 of these things. That's a lot of memory. So it's just not going to be necessary in the real world. So I'm sort of happy with it now, where it's like, well, yeah, it works pretty well. If it works well in PB, it's going to absolutely hammer inside when it's replaced in the engine. This is why I like to write things in PB, because I know the logic is better when I've got a solution that works, it's performing well in PB code. This is why, in optimization terms, it's all about identifying where your program spends a lot of time doing its calculation or doing its work for whatever the outcome that you require. Like searching through the allocations here for an appropriate place to put the new allocation is okay. This could be, if we needed this to be more performant, we could replace this in a later point, and that would have a flow-on effect with this whole thing. For this point here, probably not. If we didn't find a place to put it, we resize the heap, and then it's return this address here as the location of the new allocation. So the allocation has these two things really. We've got this. We're finding the address that we're going to give this bank, this required size, and then we insert this bank ID into the list of what banks are currently there. And that's a classic insertion sort. For our insertion sort, for those who don't know, it's kind of a brute force approach. Really, it's not that efficient actually. In this case here, because allocation in our real world situation is not that high, you might be allocating a few things a frame, and then they're not moving around in memory all the time. So our insertion, even though it's kind of a brute force approach, it works out to be fine. As you've seen in the test here, it's doing this all the time. So what it does is it steps through the array of the ordered banks, looks for an appropriate location to insert this new bank that we just allocated. So we're searching for the location, shifting anything below it, we're shifting it down, and then we're inserting this new thing into our structure, and that's it. That's all it is. But because we're doing a scan through here and doing a copy, it's not as efficient as what it could be. Yeah, that's all we're going to say. Just to believe that in your head. So if this is allocation, it means that when we delete something too, we have to actually remove it from the ordered list as well. So we can't just delete the bank. We have to remove it from the ordered list so it gets returned back to the system. And if we follow that through, where are we? Back here, deletes is free. As you can see, we've got some wrapper functions here, making it look like sort of PB code really. Does the bank exist? If it does, great. Let's remove this sorted bank from the list, and then let's release the bank. So we're kind of treating it like if it's a linked list, we would have like an unlinked process and then have something that releases the memory that this thing was this resource. So to remove the thing from our, it's kind of the inverse of the insertion of the insertion sort. We find the thing in the list for the thing we're going to remove, and we copy the stuff past that down. Now, an old trick with this stuff used to be you would just copy the end item over the thing you're inserting. That's very quick, but in this case that would break because we want to maintain things being in order. Look, the main cost of doing all this stuff is when we have to expand these buffers. If we run it in debug mode again, we might see those things coming up. Sort of allocate a bunch of stuff, up to 20 meg allocations, 50 meg of allocations. But so when we go up here, that's why we're seeing this thing resizing, by the way, because when the whole buffer gets resized, our percentage, our ratio is changing as well, because allocations are taking place in half the space they were before, because we've doubled the buffer size or the array size. It does output this data, but anyway. I mean, the main buffer gets managed up. It generally grows. It doesn't actually contract itself. There's no logic in the library at the moment to do that. But I just wanted to give you a bit of a heads up on, when we talk about optimizing applications, this is the kind of thing we're talking about. We're looking at our problem going, where is it spending all of the time? Can we avoid doing that by restructuring how we by restructuring the solution to avoid that particular problem? That's what all we've done here is we made the banks library. The old one used to put all new allocations on the heap, one after the other, and if you deleted one, it would copy all the data down, shuffle it all around and stuff, which, you know, for small buffers, which the assumption was, it works fine. But it fails when you get heaps of these buffers and lots of this data in that system. It wasn't as fast as what it needed to be. So in this case, where we're swapping the problem, really, we're avoiding moving memory as much as we possibly can just for keeping a sorted list. That's the real difference between the two. We're keeping a bunch of allocations, our allocations, in a sorted list, and we are doing a bit more logic to work out a place to allocate from the global pool of memory for each allocation, and then we're sort of running through and keeping up doing that. So the cost of the request part of the allocation is slower than what it used to be, but because we don't have to move all of the memory, that loss of performance in one part is now far exceeds the loss of performance by copying the actual data down or moving the way it was before. So the net gain is obvious. It's not pretty to look at. Just in case you want to, we'll look at this function here that visualizes the allocations, wherever that is. Just draws an image, and then we scale it up and render memory map. So I'm making a palette every time we call this thing. It's kind of a grayscale, blue scale sort of thing. The image is 256 by this. So it's quite a large image. We ask the system how much memory is available, how big is that main cache. And we make a scalar between the two. So we're scaling our number of pixels into the available memory, and that's what's going to give us a ratio between the two, so we can scale one to the other. We can map our memory allocations to effectively screen pixels on here. We ask the system, what's your biggest allocation? And we make a ratio out of that. So we're using the biggest allocation to give us, to color each one based on our palette, pretty much. So if we know what the biggest allocation is, and we look at each allocation as we step through, we can go, all right, so how big are you? And how big are you in relation to the biggest allocation? That's all we're doing. Offsetting that into a palette, getting a color, our start address and end address within this larger address space. We're scaling them from effectively from our memory space coordinates into pixel space. If you think of this, like, just imagine an image that wasn't square, that is like is 256 by 256 pixels wide, like one strip of that thing. We're sort of mapping those pixels to there, but here we've got to do it on a square image, so it's kind of clumsy. So we're scaling the start address of allocation and end address into image space. Then we're going, well, I need this to be a two-dimensional coordinate on screen to represent where this block is going to be. That's the start address, that's the end address, but these things, they might be on the same line, or they might be on separate lines, or might take, depending on how big the allocation is, right? So here I've got a bit of crappy logic that just goes, well, hey, if the start and end are on the same line, we can just use a box or a dot to represent this thing in the output. If they're not, we step through this section here, from the top coordinate to the bottom coordinate, and we fill in as a series of these rows. So it's quite quick and easy to fill. That's why it's able to render this actually in real time. The one thing we are doing though is it's quite destructive, this routine, is it's actually, every time we run this, it's creating the image, and then it's actually deallocating the image at the end, which is really ugly. And what we could do here is have, like, static temp image or something like that. So if we sort of went, well, is temp image equal to 0, temp image, and then so first time the function's called, this is going to be 0, that'll give us a new image, and then here we can just go image equals temp image. So it wouldn't allocate that every frame, which is, memory thrashing 101. We don't want to be doing that. In our main test down here, wherever this actually is again, where's that going? In that display function, this thing is actually deleting that image at the end of the frame. So let's get rid of that. We just blend. To display it, we're just drawing a box as like the outline, and then drawing a rotated scaled image. Try it again. This won't have any impact on us because it was quick enough before, so there shouldn't be a main drama about it. But that's how the memory map is visualized, which I think is actually, to be honest, it's well worth, if you're thinking about building debugging tools for your own applications, which is what this is actually doing. So I can visualize it, see it, test the logic, and then go, okay, this is how I'm going to build it. just having something to visualize what's going on is really powerful. So, you know, you might do that for your character array, or you might do that to have some sort of visual representation of, okay, where is it spending all its time? What function or what area of the code is my application spending heaps of its time doing stuff? Maybe that's where I need to spend some time tweaking up the logic, or working out, well, why does it spend so much time doing this thing or that thing? How can I restructure that to make that execute better? Getting back to what we're talking about, you know, this is the kind of thing where people ask me often about, why does it take so long to build this thing? This is the answer, because you're trying to build the most efficient system you can in every context. And when you find gross inefficiencies inside it, I like to crush those things and get rid of them if I can. They're not always possible. You know, you can't win every war you try and go into. But this is the very reason why a lot of these projects take longer than what you expect, because you end up with problems you didn't foresee that you should have really been done years ago, or just sitting there lurking underneath inside the libraries, waiting for some situation to reveal them to a user. So that's why things take so long. Anyway, dudes, thanks for listening. I'll see you next time. Bye.